pulled up this example from the very end of your notes from 5.4. So we got through everything in 5.4. We're just kind of hanging out doing a couple of the questions. We did the conjugate root theorem. You know how that works now. There's a few examples of those in your notes. I'm doing this one real quick because it kind of does look a little weird because look at the power. It's how they go down in even numbers, 6, 4, 2, and then of course none. Already wrote out, like I said, all the factors. There's our pluses and minuses. Okay. Remember step 1, find your zero. Okay. I want to show you what happens if you pick a wrong number. Okay, because I've been going straight to, hey, this works, this works, this works. If you really haven't started doing the homework yet, hopefully you have tried to do this. Notice what's going to happen if you pick the wrong number. Now, I already know what the zeros are in this, but let's say I pick, let's say 2. Okay. So I'll come over here and I just start off, I'll start right here. So I pick 2. Start writing out all my factors. Now remember, I've got x to the power of 6, but then I don't have an x to the power of 5. So I've got to put in that placeholder of 0 there. Okay. Because since I'm going down by a power, I don't have an x to the power of 5 there. How's that going to happen? I don't have an x to the power of 3. How's that going to happen? You know what I mean? So things have got to drop down to the next part. So notice I'm going to put a 1, and then I've got a 0. And then I've got a -6. And then I've got another 0. And then I've got I get lost. So 6, 5, 4, 3, yes. -31. And then I got another 0, and then I've got a 36. Okay, good with that? Now remember, you get a freebie right off the bat here. We bring this guy straight down. Let's start doing the math. Okay, so I'll get a 1 here. 1 times 2 is just going to be a 2. 0 plus 2 is 2, obviously. Then you go diagonal. Remember, 2 times 2 is 4. Okay. -6 plus 4 does give me a -2. -2 times a +2 gives me a -4. Here's a -4 there. Diagonal, -4 times a 2 is going to give me a what? -8, right? -8 added to a -31 is going to give me -39. -39 times 2, well, think about that. 40 times 2 is going to give me 80, right? So you can subtract 2 off that, and that's going to give you what? 78. Okay. Is that going to give me what? -78 though, right? So -78. And let's just be honest. Do you really have to finish that off? What's going to happen now? Are you going to get a 0 in that last column? By this point, you can tell. So notice the 2 didn't work. Okay. Now, I'm going to be honest with you. That's the long way of doing it right there. Or you could have come up here and did what? 2 to the power of 6 minus 6. Sorry. Yeah, times 6 times 2 to the 4th minus 31 times 2 to the 2 plus 36. When you do the math to all that right there, it's not going to be a 0. And so you can just go, I can't use that one. Okay. Now let me show you something. I'm going to give you a number that does work. Okay. 1 works. Okay. Now the thing about this one you got to be careful of. Sorry. Weather today. When you try out 1, okay, you plug 1 in here, you get a 0. So then you start doing your synthetic division with 1. You do it, you know it's going to work. You know you're going to get a remainder of 0 at the end. You've dropped the power by 1. You've now got an x to the 5th and so on and so forth. You need to try 1 again. Always try it one more time. Because as you've seen in this lesson, haven't you seen how you can have x plus 1 squared? Well, that means you have that means that happened twice. Okay, so that can happen. Okay, now if you do 1 and then you try it again and it doesn't work, well, okay, it doesn't work. You just get rid of it. Okay, and then maybe go on to -1. So kind of watch out for some of this in your homework. I didn't show none of these in your examples. Reason being is through the process of it, whenever it wants some of your answers, it's going to want to say, hey, you ended up with x plus 1 twice. That means you need to write x plus 1 squared. Well, then it'll ask you, hey, what happens? Is there anywhere that it goes across? Is there anywhere that it bounces? Well, if you got x plus 1 squared, what's happening there? It's bouncing. Remember that? If it's an odd number, it's going across. Kind of help you remember that a little bit? Okay, so kind of just be aware of that. So on this one right here, like I said, we'll finish this one off very quickly, then we're gonna jump into 5. We got x to the power of 6, so I've got a 1 here. And then rewrite everything. Notice I have 1, 0, -6, 0, -31, 0, 36. I get that freebie of 1 there. Bring down the 1. 1 times 1 is 1. That's going to give me a 1 there. And that gives me a 1. And that's just going to give me a 1 there, correct? Which is going to give me -5. Put a -5 there. -5 right there. Come back up here, put a -5 here. That's going to give me a -36. Here's going to give me a -36. And then hopefully you're going to see that, look, you get another -36 here. And then you're obviously going to get a 0 at the end, right? Okay. So you come in here, you put your -36, you get your 0. Now hear me out again. Just because you know during this math here, up here, you got that 0 that you wanted, doesn't mean you get to skip out on the synthetic division. You got to go do it because you got to take that factor you know of to bring that whole polynomial down by a power. Because remember, the goal is to do what? Why are we doing this? Just for the fun of it? No, to get that to where we can get it to what? So we can get it factorable. I cannot factor that. There is no way, there is no formula out there that you're going to find, even on the internet, to look at this one right here and go, huh, now how would I factor that? That one maybe, I'll be honest, that one possibly, you could probably group it because it is only 4 terms. Maybe, maybe not, you know, but this is still the process, okay? Now, had that had all the deals on it, think about it, that's 7 terms if you add the constant. You're not going to be able to factor that, okay? So notice we found a 1. Now, on this one, I'm going to tell you right now, I can tell you another 1 doesn't work, okay? But remember, right here, this worked. So I'm going to rewrite this, and I suggest you start doing the same. I'm going to rewrite it with that factor in it. So how did I get that 1? It had to look like what at some point? Negative. Well, it had to look like x minus 1, okay, equals 0. Remember, we're making it equal to 0. So I know a factor right now is going to be x minus 1. And then I rewrite everything. Notice I've got a 1 here, so that's going to give me x to the 5th plus x to the 4th minus 5x cubed minus 5x squared minus 36x and then minus 36. Now you're back at square one again. It's like an algorithm, okay? You're back at square one. You got this whole big old list of numbers. You've already tried one. Now you would try one again. At this point, you try it again. Because remember, you can have one happen twice, which is why you end up with those like x minus 1 squares. Okay? Like I said, with this, I'm telling you right now, it doesn't work. Saving us a little time, okay? Because I need to get into 5.5 today. But you need to try it. Okay? It's not hard. You're literally just plugging it back in. Okay? You start going with your numbers again. Get out your calculator. Nope, didn't get a 0. That one number doesn't work. Okay? So, the next number that does work, -1. So notice, really, you're 2 numbers in, you've already found 2 numbers. If you're testing numbers and went in order, you've already found 2 right off the bat. So come in here, and I know that -1, okay? Then write your coefficients again. Okay, I got 1, 1, -5, -5, -36, -36, 1, 2, 3, 4, 5, 6, 4, 5, 6. Remember, I want to make sure that I don't have any gaps, right? I got to make sure that I have 5, 4, 3, 2, 1, 0 as far as my power, right? If there's any place that I'm missing a power, What do? Add a 0, okay? We get a freebie right off the bat. Get a 1. 1 and -1 gives me a -1. That's going to go to 0. 0 times -1 is going to give me 0. So that just goes to 0 there. And that's going to give me a -5. Negative and a negative make a positive. And so that gives me a +5. That goes to 0. This will go to 0. I got a -36. And you can see this is going to work. We know it's going to work. I'm telling you right now, you should know it's going to work. Because what happened up here, when you tried -1, what happened when you plugged it in up there? You got 0. If you're just willy-nilly plugging in numbers and doing synthetic division, why are you doing that to yourself? Plug it into the formula work. You know it's going to work before you start the synthetic. You're just doing the synthetic to get your new polynomial. That's all you're doing. Okay? So yes, of course, negative and negative make a positive. There's my 36. And there we go. What do we have left now? Now, notice how I'm going to rewrite this. I have, well, x minus 1. But then I have what now? X what?
+1.
Exactly. I have x plus 1. Right? Because to get that -1, it had to be x plus 1, solve for 0, or make it equal to 0, you get -1. But then I've got a brand new polynomial. Notice I have what here? I've got x to the power, I had a power of 5, now what do I have?
4.
Power of 4, exactly, so I'm going down by 1. X to the power of 4. I do not have an x to the power of 3 right now. Okay? So I would say no 3, but I do have a minus 5x squared. I have no x, but I do have a constant of plus what? Sorry, that's a -36. It does. I don't know why it does it on this computer. Minus 36. Now that one right there is technically factorable at that point. Okay, I'm gonna tell you why, because you did learn, I believe in chapter 3, when you have something of polynomial-like equations, remember how you can kind of change those up? But let's just say, for giggles, you're like, man, I don't remember how to do that. Okay? You can do synthetic division again. You can go, okay, hey, I've got a smaller one. And remember, you don't always have to put these back in. I mean, I always go back to the original one, the original guy, to see what works. Okay? But think about it. If you plug in a number here, it should work, right? Yeah. I'll give you another number then. The next one, now we know 2 doesn't work because what happened whenever I tried to do synthetic division with 2? Literally, just doing synthetic division with 2, I didn't test it. I came in here and went, oh, 2 doesn't work. Look what happened. So I can skip right by 2. But the problem is, what could work? -2. I'll tell you right now, it doesn't. Okay, save you a little time. -2 doesn't work. 3 does. Okay, so we can come right in here and go, well, okay, now let's do this again. We put in the 3, so notice we've got a leading coefficient of 1, but then I got to put a what? 0. And then I've got a -5, and then a 0, and then a -36. I get my freebie, bring it down, I get a 1 and a 3. A 3, and then a 9. -5 minus 9 is what? -5 plus 9, I'm sorry.
4.
4. 4 times 3 is 12. Get a 12 here. 12 times 3, 36. I know it's going to work. This should not be a surprise. I got to emphasize that. It should not be a surprise to you that you're getting a 0 right here. Because where should you have already tried that 3 out? In your equation. You're just doing this part to get the power lowered because you're trying to get this thing factorable. To get it to a low enough power that you can go, I can do AC method. I can do quadratic formula, completing the square, anything. Grouping, okay? It's just that powers of 6, you're like, I have no clue. Powers of 5, I have no clue. Powers of 4, maybe. like earlier, could you? Yeah, that was in a form where it's polynomial-like. Okay, but now we can rewrite again. Once again, writing all my factors now. Let's come in here and look at this, and I've got x minus 1, x plus 1. And then I've got what? X minus 3. And then I've got still the polynomial. But notice now I've gone down a power again, haven't I? So I was at a power of 5, then I was at a power of 4, now I'm at a power of what? 3. So notice I've got x cubed, there is no x squared, plus what? Oh, there's, I'm sorry.
There's a 3 with you?
I'm looking at my 0 there. I'm like, there is. So then I've got a plus 3x squared plus 4x plus 12. Well, let's be honest. Let me write that a little larger right here at the bottom here. I've got x cubed plus 3x squared plus 4x plus 12. Have we gotten into a point where we could probably factor this now, not have to do any more synthetic? I've got 4 terms. How about I go ahead and come here and just group them? Okay. Notice on this first term, I can pull out x squared. Okay, and that's going to leave us with x plus 3. The next one I can pull out a 4, and that's going to leave us with x plus 3. And then notice what we have here. If I write all this out, I've got x minus 1, x plus 1, x minus 3, x plus 3. And then I've got this x squared, what?
Plus 4.
Plus 4. And can I find the zeros to all those? Yeah. Problem is what? Everybody's got a 0 except for what? That last one, right? Because it's what? What's that going to turn into?
Complex.
A complex number. Which is why this question says this. Use the conjugate roots theorem. That's all it's saying, hey, whenever you get done with this, guess what? You're going to end up with a complex number, which means I'm going to end up with x is equal to negative 4i, which means I'm also going to end up with what?
Positive
4i. We're always going to have that positive negative. And there you go. Now, how many answers should I have gotten?
6.
6. How many did I get?
6.
6. I've got this one, this one, this one, this one. Now, let's be honest. You're going to get one. How many times, hear me out, how many real zeros do you have? 4. How many times is this going to go across the x-axis? 4. It's going to go here, 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 and here. How do you know that? Just knowing it by what you learned.
Change its signs.
Nope. Look at the power. Odd powers go across the x-axis. If they're, like, let's just say, like I said, when you start doing this on some of your homework, do you mind if I just write down a fake one right beneath this? Let's say when doing this process, you ended up with something like this. X minus 1, and then you try out 1 again. Like I told you to, 1 can happen twice. So then you try it out again, x minus 1, x minus 1. Well, doesn't that turn into x minus 1 squared? So notice that would be what we call a what? Think about it. A bounce. Yeah, it doesn't go across, it bounces on the x at 2, right? It would come up and just bounce it. It wouldn't go across, it just bounces. Okay? Everywhere though it's even, odd, it goes across. Anywhere that it's an even number, it's a bounce. What would happen? What would I say? It goes across. What would I say if this happened? Where would it flatten out? Anywhere that's greater than or equal to what? You remember what flatten out means? Look at that. That's x squared, right? What would x to the 6 look like? Would it look like this? Remember that? So anywhere what? The power is greater than or equal to what? 2, exactly. Here, yeah, it just bounces. But as this number increases, even, okay, even doesn't matter, just gets larger, it's going to start flattening out at the origin. Okay, you're going to get wider and wider and wider. Granted, you can have translations up and down. That can help you. I remember that. Let's go back and look at the previous notes and you'll see that. Good? We all right with this one? Okay. Math gets a little messy. Look at the notes. Okay. It's just messy because it's tedious. It's gotta do a bunch of foiling. I ain't even gonna lie. Sometimes that's it in this class. If you're really, really comfortable with your foiling, and you know you're comfortable with your foiling, okay, comfortable enough that you can go, dude, I can foil in my sleep and I'm not even worried about foiling on my midterm, or my final. Then yeah, use one of those softwares to help you foil stuff quicker so you can get to something else in the problem, okay? Mind you, you're not gonna have that on your test, okay? But if it helps speed you along on your homework, I'm all for it. I'm all for software like that if you're comfortable where the software is helping you, okay? So just kind of think that. We good? All right, guys. You literally at this point, as of right now, know how to factor any polynomial I throw at you. 6, 7, 8, 9, 100. Yeah. But you could do it. You'd be mad at me, and it'd probably take you all semester. But you could literally factor something x to the power of 100. I would hate to do that. I wonder if your brain could handle that. Yeah, you'd probably make a mistake. You ever see these guys try to calculate pi by hand? Never works out right. Newton did it though. Up to 32 decimal places, I think. So, anyways, there you go. So let's finish up with 5, 5. Okay. 5, 5 is not as bad as what it looks. Rational functions and rational inequality. Rationals just means ratio. Ratio just means what? Fractions. Okay. So remember chapter 14 in intermediate algebra, whenever you started seeing polynomials above polynomials, and then probably during that whole class, you're like, why are we even doing these? Here we go. That's why you're doing them. So now that the math on this is actually pretty simple, okay, because it's going to be stuff you've seen before. They're not going to make it too hard on you, so don't worry. But mind you, we're not going to be just dealing with powers of 2 anymore. You could deal with powers of 4, couldn't you? Could you factor that? Yeah. Unfortunately, you got to say yes to everything now. There is nothing not factorable for you at all now. Okay. So looking at this question right here, and I'm going to go through this first part pretty quick because once you learn the picture, you're going to be like, okay, the hardest part is actually the graphing sometimes. Okay. Because you got to throw in test points. Okay. And that gets a little annoying. But notice a rational function is a function that can be written in the form f of x is equal to p of x over q of x, where p of x and q of x are obviously polynomial functions, and q of x cannot equal 0. But there's a caveat. Even though q is not allowed to be identically 0, there will be often values of x for which q of x is 0. That's basically saying you may get a bunch of answers. Because it's saying, remember, we're dealing with a function now, okay? Which means I can plug in any x I want. But there are some specific x's I can't have. Remember, restrictions. We're just not going to call them restrictions anymore. Okay? You're beyond that now. It is usually at this level in intermediate algebra, I started toying with the idea of going, hey, I'm going to start treating you like college algebra students because you're basically almost there, right? This is basically calculus right here. This is very low level. I'm not in the water yet, but I can see the ocean kind of calculus terminology that we're going to use today. Okay. Hence why your book is not called college algebra. What's it called?
Pre-calculus.
Pre-calculus. Okay. Irony. The math for calculus for a lot of this is easier than the math you have to do in college algebra. Okay, that's the sad part, is because some of these I actually had to stop and remind myself, oh, hold on. You're teaching a college algebra class. You're not teaching a calculus class. Go back. You know, because a lot of stuff you can do in your head in calculus. Literally, it's like, oh, that's it. Just write it down. But it's not me trying to push calculus. So just saying, you want easier math? There you go. A lot more weird signs though. That's what freaks people out. Look at these right here. Notice we have all these little lines here. Hey, what kind of graph is that? Anybody tell me just by looking at it? What should it look like? 1 over what? X. Very good. Okay. 1 over X, you know that because it's got a what type of power? Odd, exactly. Very good. Okay. So notice these right here. In either one of them. Now this would obviously be one that's been translated what? Up and to the side. But notice these lines kind of followed along with it. Okay. Keep that in mind. I'm going to read some examples. You don't got to write them down. You can go back and print these off. Okay. I'm going to show you many examples of these. Vertical. Okay. Vertical asymptotes. Vertical. Okay. Vertical, the line is line that x equals c is a vertical asymptote of the function f if f of x increases in magnitude without bound as it approaches c. Examples of this I'll show you shortly. The graph of a rational function cannot intersect a vertical asymptote. Horizontal asymptotes, like a horizon. The horizontal line y equals c is a horizontal asymptote of a function f if f of x approaches the value c as x goes to. Now that little line there, everybody remember what that arrow means? Means approaches. Okay, that line means approaches. It's basically saying, hey, as I decide to make x larger and larger and larger going in the negative direction, okay, this is what's happening, okay? Or if x approaches positive infinity, this is what's happening, okay? That word approaches is really important in math because I can't divide by 0, can I? But I can see what happens to a function if I get infinitely close to 0. Does it go to 0? I don't know. Maybe it doesn't. The graph of a rational function may intersect a horizontal asymptote near the origin, but will eventually approach the asymptote from one side only as x increases. You'll see a picture of that. Vertical. It will never cross that asymptote. Horizontal though, you may see a line do this, like it may come down and then come back up, go up and then come back down. And so you'll see it cross that asymptote, but then it'll do this and start approaching it at that point, okay? It's because it's not a restriction. Vertical asymptotes cause restrictions, cause undefined. Remember what we said? Hey, vertical lines, if you try to find a slope of vertical line, what is it? Undefined, right? That just means the slope is 0. Okay. Oblique, slant. The more annoying ones. A non-vertical, non-horizontal line. I love our math terms. Okay, because I'm stupid. I'm like the not vertical and the other than. No, some math you got. No. We got to make this sound even harder. May also be an asymptote of the function f. Examples of oblique or slant or asymptotes appear in figure 4. I'll show you. Again, the graph of a rational function may intercept. Okay, it's just saying, hey, when you have a line like this, your function may intersect it, but it's going to turn or do whatever, and it's going to approach it. Okay. While these may seem weird, let me show you some examples. And then let me give this asymptote notation real quick, which you should know. The notation x approaches c. Notice that little superscript negative, okay, is used when describing the Hager graph as x approaches a value, some constant coming from negative infinity and approaching that number. Okay? From the negative side. Hear me out. This does not mean it's going negative. It means it's coming from negative toward that number. So you know which side of the function you're looking at. Okay? So if I'm looking at a function here, here's my line. It's coming from this direction, and I know that because of that negative c. And then I don't know what's happening over here. It could be going up, it could be going down. And then the opposite is true for c plus. Okay? Technically speaking, okay, now technically speaking, if you see this notation here, c, it's because this is happening here and here. So we don't write it twice. We'll just say, if I see x approaches c, I know it's approaching c from both sides. Okay? We usually use the superscript negative or positive if it's only happening on one side. Okay? That's more of a calculus thing right there, because some things may have what we call a limit coming from one direction, but not from another direction. Okay? You don't gotta worry about that too much right now. Okay? Are you good? So far. So it's all definition. It's not as bad as what you think. I'm serious. It's not as bad as what it sounds like. So look here. I have some different types of asymptotes here. Notice I have a vertical asymptote. As x approaches negative infinity, as x goes to as x gets really large, right? As x goes where? This direction, right? Well, what's going to happen to my y? Y is going to do what? Approaches -2. As x approaches -2, the closer x gets to -2, or coming from the negative direction, I get this asymptote. Okay? When you see the formula, it's going to make total sense. You've already done it a lot. Notice this right here. As g of x approaches negative infinity, x approaches 2. That's its asymptote. That would actually be a restriction. You will never see this cross. Okay? Now notice this horizontal one here. This could cross here, but then this still would be your horizontal asymptote. They would still tend toward that line. Okay? This one wouldn't because of the type of graph it is. And then here's your different types. You have a vertical. You have horizontal. Notice what I've been talking about right here. Look at that one. Doesn't it cross that red line? But what does it do right after it crosses it? It starts to tend toward that line again, doesn't it? That's what happens. Okay? Because it is allowed to do this, this should tell you right here that this line is not a restriction here. Don't think of that as a restriction. Okay? It is an asymptote. Okay? But it's not a restriction. You're totally allowed to have one of those. You can have, that is obviously somewhere that could equal something, right? It's just something happens there at that line, and that's okay for that to happen. Here, though, on the verticals, you can't have that because that would make the function undefined at those vertical asymptotes, okay? And then you will have oblique asymptotes, which once again are allowed to cross. Notice this one right here. That one does cross, but it does tend toward a line. It tends toward, what type of line do you see there for that asymptote? Nope, just the line. We're just looking at the line. I'm not worried about the function. Look at the line that it created. Look at the asymptote. What type of function would that be if I graph that?
Linear?
Yeah, linear function. What kind of form is that? How do you make a line? y equals,
mx plus b.
there you go. That's just a line with the slope. So it is. You'll see it. I want you to see that now, so that way when we solve for an oblique line, you're like, oh, I get it. I just made the equation y equals mx plus b, because that's going to always be a slope. That asymptote's not going to change. It's always going to be that line, that slope. Every other number has a y equals this, x equals that, because they're either vertical or they're horizontal. Isn't that why you learned all those? You probably wondered why. Well, there's a lot of reasons why, but this is another reason why. Now you've got a slope. Well, the only way to have a slope, equation of a line. Okay? Good? So far? Okay. Equations for vertical asymptotes. Look at this one right here. Find the domains of the equations for the vertical asymptotes of the following functions. Look at A. Well, remember, a vertical asymptote is basically anywhere that guy cannot equal what? Look at it. Yeah. Look at the first one. You're just finding a restriction, aren't you? Okay. If you want to call it a restriction, right now we're actually finding asymptotes. Okay. Notice for this A, I would come in here and go, okay, well, I've got f of x is equal to 32 over x plus 2. I know x plus 2 cannot equal 0, so x cannot equal negative 2. Well, y'all all know what this graphs into, okay? Remember, it graphs into that one that looks like this, one part's going up, another part's going down. I'm just going to give you the base graph on this one. Don't think it's like perfect, but if I drew it, can we all agree negative 2 would be right here more or less, so that'd be where x is equal to negative 2. And so therefore I have a graph doing this, which is why your domain is negative infinity all the way up to what? And then what? Yep. But notice the next one. Well, first off, you got a factor. So I've got x squared plus 1 all over x squared plus 2x minus 15. Well, let's be honest, let's go and just factor that guy just really quick here. Knowing I got a pretty coefficient of 1. Different signs, larger one is positive, smaller one is negative. What two factors will give me to positive 2 and multiply to negative 15? Exactly. How about 5 and 3? Hey, 5 minus 3 gives me 2. 5 times negative 3 gives me negative 15. But doesn't that mean I have a restriction or an asymptote now? I have an asymptote where what? X cannot equal what? Negative 5 and 3. Now here's the problem with this one. They're a little bit harder to graph. But we'll tell you this though. You have this here, you have an asymptote there. You also have an asymptote right there. So we have one at negative 5 and one at 3. Your graph technically for this one would look like this. You'll learn how to graph those. In Hawks, you're going to be picking pieces and putting it in there. And the only way really to do it, test points. Find out what's happening where. Okay. But notice you still have a domain, don't you? Am I not going to negative infinity? Right? But then I'm going to where? Yeah, and I can't equal it, right? But then I'm going from where?
Negative 5 to 3.
Yeah, negative 5 to 3. But I can't equal that either. So I put another unit, and then I'm going from 3 to infinity again. So there's your domain. Horizontal and oblique are a little bit harder. Okay, so you're probably gonna, You can write down the whole thing, or it's really up to you, or just kind of pay attention. Okay. Like I said, these are all going to be in your notes, obviously. But you just got to remember some things. I'm going to read these to you, but I'm going to show you the examples. Okay. Equations for horizontal or oblique. Basically, what it's saying here is you've got two polynomials. Now, hear what it says. The p of x is an nth degree polynomial, and then the q of x is an nth degree polynomial. They've just changed your leading degree so that way they can have two different degrees. Okay, so you have a way to differentiate them. So notice, if in my numerator degree, okay, leading, okay, the degree of the polynomial, my n is less than m, okay, the horizontal line is at 0. Like if I had x squared on top, x squared and some junk all over x to the 5th and some junk. Well, n is less than m, isn't it? Immediately, my horizontal asymptote is 0. Y equals 0. Immediately. If n is equal to m, I have x squared over x squared. Doesn't matter it does not matter all the junk. Okay, it doesn't matter if they are the exact same. You're literally just dividing your leading coefficient by your leading coefficient. And then that will become your horizontal asymptote. Okay? If n is equal to m plus 1, okay, that'd be like saying if this was a 3 and this is m is a 2, well, 2 plus 1 is equal to what? The 3. They're basically one away from each other. Okay? If n is equal to m plus 1, the line is an oblique asymptote, and then guess what? We're going to do some division. We're going to do some long division, not synthetic. We're just going to do long division. Take the bottom guy and divide it, right? Take the top divided by the bottom. You're going to end up with an equation, and guess what the equation is going to be? The equation of a line, because it's oblique. Okay, so you're creating a y equals mx plus b there. And then if n is greater than m plus 1, there is no straight line, and there is no horizontal or oblique asymptote. Look at the one we just did. Okay, well, this one right here, this has equal. Okay. The neat thing about this one is, look, x and 2, aren't those the same? What does it say here when you have x and 2 and they're both exactly the same? Doesn't that just mean when n and m is equal, you get a horizontal asymptote? Okay. I have one. You're going to have one there. But then I can take it and divide them. Well, that works. So, let me show you some examples. Look at all of these. Notice if n here, what is that? What are the n's? Are n and m equal? Yes. N is equal to m, which means if I decide to graph these, I would look at this and go, okay, if I need to find a horizontal asymptote, guys, you already got a vertical. Do you realize that? On this one, didn't we find the vertical asymptotes? This one's telling you, you also got a horizontal one. Okay, well, where's it at? We'll just take this x squared and divide it by x squared, because doesn't it say just divide those? It doesn't matter what else is happening, just divide your leading coefficients. And what are you going to get? Well, x squared divided by x squared is just 1, which means my horizontal asymptote is going to be where y is equal to 1. So I have some verticals at what? On this one was what? -5 and 3. But then I also have another asymptote at where? 1. And then it's at that point, once you find your asymptotes, I'm kind of giving you a little hint about graphing. You find your domains, right? You don't worry about this. You just find your domains and you start picking test points. Going, what's happening to x over here? Find a couple. What's happening to x over here? Find a couple. What's happening to x in the middle? Find a couple, and then you're just going to drag and drop pictures. Okay, I'll show you an example one. Okay, look at the next one. My leading coefficient, my leading degree, or the degree of the polynomial on top is a 3. Okay, the one on the bottom is a 2. Well, notice, can I add 1 to that 2 and get a 3? Okay, so notice on this one I have n is equal to m plus 1. This one I'll show you shortly how to do. But this would really be 1, since it is going to be an oblique asymptote, you would really have to do this. X squared plus 9 and divide it into the x cubed plus x squared plus 2x plus 2. Do your long division. Okay, you cannot use synthetic on this one because it's not of the form x minus c. Okay, but notice on this one right here, you would come in, do your division, and then what's going to happen at the end is you're going to get something of the form y equals mx plus b. Okay, you're going to get an equation of the line. That's your asymptote. Notice the next one. Okay, n 4 is less than 6. So n is less than m. Anytime that happens, okay, you automatically have a horizontal. And what's nice is that happens, it's always going to be where y is equal to 0. Just the x-axis one. The next last one, you've got, look, n is greater than m, but you don't have one that's just like that. You have n is greater than m plus 1. Okay. Notice on this one, if you remember, n greater than m plus 1 says you do not have a straight line. Okay. Horizontal or oblique asymptote. So no oblique or horizontal asymptote. No. You will only have the verticals. Okay, that's all you'll have. Hear my words. You're always going to have vertical asymptotes. How do you know you're going to have vertical asymptotes? What's another word for these vertical asymptotes?
On the bottom. Variables on the wall.
Right, but what is a vertical asymptote? What did I call it? Yeah, they're restrictions, right? The vertical asymptotes cause restrictions. They cause places where that function is going to become undefined, which is why that function never crosses those. In the horizontal and in the oblique, that function can cross those. It doesn't care. It's like, I'm going to cross these. I'm just going to tend toward a limit at that point, or tend toward that, okay, equation or that line, that asymptote. Everywhere else can't cross it because here, hey, guys, that's x plus 5, x minus 5. That's the difference of squares right there. That means I cannot equal what here? -5 or +5. Because if I do, I get a 0 in the denominator. That can't happen. But hear me out. With your horizontal or even your oblique asymptotes, what it's saying, if you plug in a number, you're going to get a 0. Okay. Well, what happens if this goes to 0? The top. What's going to happen? What's 0 divided by anything?
0.
That's okay. 0 is a number. We're okay with 0. If 0 happens here, though, we got a problem. It's undefined. Can't do anything. So you notice the difference between the vertical and the horizontal and the oblique, okay? That's how come things will look that way. You okay? So far? Inequalities. Solving rational inequalities. They're of the form of this. It's the same as what you've seen, except they're going to be rationals. Okay, you've seen this before. You've already done these before. Remember, that's whenever we drew that real number line and said, okay, let's do some test points. From here to here, is it going to be strict or not strict? Okay? It's just now we're dealing with rationals. And you're going to use the same tools I taught you for rationals as you did in intermediate. You're going to have to find common denominators. Okay? Put the formulas together. And then see what works. I am not going to lie to you. Learn the math on this and then go into Desmos. I'll show you in your notes. I don't have it on these notes right here. In your notes, I actually graphed a couple of these in your notes on Desmos and have the pictures in your notes. And you can see what it looks like. Okay. Let me show you an example of one. First off, I'll show you all the instructions, which you do not have to look at, and all of you don't want, because I'll show you how to do these. Let's look at this one right here. Notice we have this. I want you to be very careful here. This is a little bit different. You've got to find all zeros, top and bottom. Now, only real zeros. You're not looking for complexes because you can't graph those. Can we all agree that there's no real zeros in that numerator? If I tried to solve that right now, what's going to happen? I'm going to get x is equal to plus or minus I. So you don't got to do anything to that top one right now. But I do have some zeros on the bottom. Do I not? Okay, so we got to solve for those again. Notice we already did this when this one turns into, okay, I've got x squared plus 1 all over, was this x plus 5, x minus 3, which means I have zeros at what? Negative 5 and 3. Okay. So once again, you're going to come in here and do this. Draw yourself a little line. And notice I have negative 5 here, and then notice I have 3. Which means I have some domains, don't I? Okay. Be careful of the sign. I really want you to hear that. Be careful of that sign. Because remember, if you can come up with some zeros up in your numerator, you got to count those in. Where your zeros happen in the numerator, you're allowed those numbers. They are not restrictions. Okay? Remember that. Okay? So if you start getting like these really weird bars or whatever, like red bars in Hawk, but you know you're doing the math right, first off, go look at it and realize, oh yeah, I had a real number. And I'll show you one on an example. We'll get through this one pretty quick and then I'll do that example. I'll have to leave the rest of the examples for the notes. But look here. You're going to graph. I'm going to do this very quickly here. Notice I have a domain here from negative to negative 5. Negative 5 to 3. And then what? 3 to infinity. And then all you're going to do, now hear me out. You find test points and you do it. Where is it true? Does that make sense? Okay. So notice, like I said, very quickly, just to kind of show you one, if I do f of negative 6, well, that's going to equal negative 6 squared plus 1 all over negative 6 plus 5, negative 6 minus 3. Doing the math of that very quickly, I'm going to end up getting 37 over 9. Is 37 over 9 greater than 0? Yes. Okay, I'm like, uh-oh. That one works. Isn't that what the inequality is asking for? It's saying, hey, is this find values of x that make this greater than? So all you're doing is plugging it in, right? See, does it work there? Yeah, that works. And then I would try out something in here, wouldn't I? And then I would try out something here. And wherever it works, that would be your domain. So notice, I'm going to give you the answer to this one so we can get to the harder one. F of x is greater than 0. Well, I know it worked at negative infinity to negative 5, but also it's going to end up working at 3 to infinity. Let me show you something. if you come in here. Your x. X squared plus 1, and then we've got x squared minus what? 2x plus 15. 2x minus 15. There's your graph. Okay, but notice what I'm gonna do here. That's just your graph, right? But look what I can do here. Let's take out the y. Gives us still a nice little function, but then I can go down here to this little key down here and look, what does it say? Hey, greater than what? Oh, well, look at what happens here. What's that number? -3 to where? Infinity, isn't that what we just got? Come over here, where to start again? Oh, look, 5 going where? To infinity. I think I wrote this wrong, didn't I? Oh, I did. That's supposed to be a plus over there. There. Notice 5 and 3. Notice what you would have here if there was an equal sign is right here along this edge. You would see like a deep red line, like they would draw a specific line there. Okay, that means or equal to in Desmos. Okay, this one doesn't have that hard line. That means, hey, this is going to get infinitely close, okay, to 3, but it's never going to touch it. If we actually zoomed in and kept zooming and zooming and zooming, you would see that's not touching. Okay, but we could never zoom enough because it's tending toward where? Infinity. Okay, and so we can't zoom in infinitely close. Okay, and so that's how you can check your answers on Desmos real quick. Okay, or unfortunately, I just showed you how to cheat through your homework. But I'll get you on your assessment. I'm not on your final, so don't try not to do that. Okay, great way to check your answer. Okay, are you good? All right, let me show you. Graphing very quickly is very simple-ish. More annoying here. Very quickly, I'm gonna do this very quickly so I can get to this kind of a harder question. Notice here, I have x squared minus 49, which means I'm gonna have a vertical asymptote at where? How many am I gonna have? Factor first, factor everything first. Is that not a difference of squares? So that's gonna turn into what? X plus, x minus. So x can't equal 7 and very good. So notice, come over here. So I'm gonna have a asymptote there, and I'll have, yeah, right here. Asymptote there. I would put down 2, and then literally you're gonna go there with your finger, like your little cursor, and just click where, and it'll draw a straight line for you. Okay. And then it says this, hey, how about that? Well, guess what? Is my power on the bottom definitely greater than my power on top? My power on the top is x to the what? 0. There's not one. So it's definitely greater. And if you go back and look, anywhere that m is greater than m, y is always going to equal 0. And so I automatically have just one asymptote right here at 0. And so I have 1. Good with that? Now the harder part here, which I'm not going to, I'll show you sort of. Notice here it says this, and this is how it's going to work in Hawks. It's literally saying this, hey, you got to go in here and graph this. Now guess what? You go in and check it on, you can go in there and check it on Desmos and see what it looks like. But once again, how are you going to do it on your test? Okay. The only way I can say is you got to have some test points. Okay. You're going to have to go in here and go right here. What happens whenever I pick a number that's less than -5? Or sorry, less than -7. I'd pick a couple. And then you're gonna say, what happens whenever I pick 2 or 3 easy test points between there? Where do they show up? Okay, and I usually tend to pick them pretty close to my vertical line, and maybe one dead center. Okay, like probably a 0, right? But then I'll get one at like negative 6.9 or 6.8. And then I'll do one at like 6.8. Okay, putting it into my calculator, just finding test points. And then I'm gonna look at one for greater than. When you graph this one, you get something that looks like this. So literally, you would just come in here, and on your notes, I literally color code it for you. I go, look, I picked this one for there, this one for there, this one there, and you literally are just dragging and dropping. And it's going to do all the graphing for you at that point. You're just looking for the shape. Okay, so I'll kind of show you how that works out. On your test, do it as good as you can. If you just give me a quick sketch on your test, I'm not going to be uber like, you better show me exactly points. Man, but at this point, if you can't graph, you deserve to take this class again. Okay? Just show me a quick sketch. Yeah, I've got an idea. Now, realize that the base graph of x squared is going to be, is this guy. It just got split. Okay? But to be honest, there's no quick, easy way. It's just going to have to be test points. And use your calculator. Don't spend a lot of time. Use your calculator, plug it back in. Okay? Word problem. Population of stray cats in a small city follows this formula. P of t is equal to 350t all over 2t plus 1, where t has to be greater than or equal to 0, represents the number of months since the first stray cat appeared. What happens to the stray cat population in the long run? It's literally saying this. As t gets larger, what's t going to be? Well, what are these cats going to tend toward? What number? Well, realize that you have this. You have n is equal to m, which means this. You would take your leading coefficient of your top, which is just going to be the 350t, and divide it by your leading coefficient on the bottom, 2t. And that's going to end up to be 175. Very quickly, let me explain this. T is going to get large, right? Is that what it's saying? As t grows, as the number of cats do their business, okay, and they start having babies, and those babies do their business, and those babies have babies, and they keep doing their business, you would think those numbers would just blow up to infinity, wouldn't it? Well, then how come deer stick around? Even if people didn't hunt, now the deer population will get large, but how come it just doesn't just blow up to infinity? Well, because infinity divided now unmathematically, I'm gonna say it's very unmathematically, so if somebody ever listens to this on YouTube, they're like, you said that wrong. No, infinity divided by infinity, we can kind of cancel some of those out. There's gonna be an equilibrium happen. So notice 350 times infinity, who gives a crap about that infinity? Right? 2 times infinity, that's still a pretty big number, right? That plus 1 doesn't mean anything. So basically what we're saying is like, let's just take now, mind you, that 350 times infinity is a lot larger. That t 2 times infinity is pretty large. Well, let's just get rid of the infinity parts and just worry about that 350 and 2 because these other parts are just going to work everything out. Okay? The plus 1 is just there. It's like, does it really matter? I say, hey, you got infinity money. Here's $1. Did it do anything to that infinity at all? That's something we don't think about that. Okay? That's a calculus. That's a calculus lesson for you. And then, let me see here. Last one. I'm trying to see if there's a hard one. That one's easy. Let me show you how to solve one of these guys right here. Just very quickly, okay? All the other ones, if you look at the note, they're very self-explanatory, but let me show you how to solve an inequality, okay? First thing you gotta do, gotta factor. This one's already factored, right? But you gotta factor everything. Everything. Okay? So like I said, very, very quickly, should I do this one? What I'm trying to think. Yes, okay, good. This is the one I want to do. Okay, first off, just like any other time, you got to get it equal to 0. So you got to get one of these to the other side. Okay? And put a 0 there. So notice this is how I'm going to write it. I'm going to get x plus 3, x plus 2 minus x plus 4 is less than 0. Are we good with that? Okay. What's the problem with both of those? They have a different what? Take fractions. Denominator. Got to common denominator. Okay. So you got to come in here. Over here, I'm going to do x plus 4. What I do to the bottom? Do to the top. Over here, I've got x plus 2. Once again, you're in algebra still. What you do to the bottom, do to the top. Dot, dot, dot. You're going to clean all this up, aren't you? Can y'all do that okay? So if I skip to the cleanup part, you can kind of see what just happened. Okay, so notice what you're going to end up having here is, after all the cleanup, now mind you, that's me foiling that x plus 4, x plus 3, foiling that together, distributing that negative x into that parenthesis, and then pulling everything together. There's going to be some cancellations in there. I end up getting 5x plus 12 all over x plus 4, x plus 2, x plus 2. All is less than 0. Now I need every single 0 I see. Well, there are some automatically that you should be able to see right away. What are they?
-4 and -2.
Yeah. X is equal to -4, x is equal to -2, but there's another one as well. -12 over 5. Don't forget your numerator. This is how hard this is. Watch what you're going to do. Okay? And I'm going to do this kind of quick, because I've only got literally like 4 minutes. I need to start finding out, where does f of x, where is it less than 0? Well, draw yourself a little longer here. Okay? Notice I have -4. And then right here, I'm going to have -12 over 5. Then I'm going to have -2. Okay? Well, you've got some domains, don't you? Negative to 4. -4 to -12 over 5. -12 over 5 to -2, and then -2 to infinity. You're just going to start plugging in test points again. Remember that? And where it works is where it matters. Notice on this first one here, if I do f of -5, when I do f of -5 and finish up all the math to that, I get -13 over 3. I'm just plugging that -5 back into my equation right here, aren't I? Doing the math to, well, hey, is -13 over 3, is that less than 0 there? That works. That's what you're doing, isn't it? You're going in there and checking every single one of them. You go in, you check. If it works, that's one of your parts. You do the next one, you check it. If it doesn't work, you don't include it. So when you do the math to this one, you're going to end up getting f of x is less than, okay, 0. Well, where? Well, I know at -infinity to -4, but also at -12 over 5 to -2. What else could you find that out? Could you do that in Desmos really quick and just check your answer? Yeah. Okay. But you're having to include this guy as well. Okay, sorry, this guy right there. You have to include your domain on top, okay, because it might create something. Okay, so be real careful with that. Good? Everything else in your notes, a lot of the ones, trying to see if there's any of the weird one, there's really not. The only weird one you might find a little weird is the asymptote one right here. Right here, but you're literally just gonna come in and do the long division. On that one, do x minus 9. On this one, could you do synthetic division? Look at the form of the denominator. Isn't it of the form x minus c? Yeah, you could do synthetic division on that one if you wanted to. If you don't have it in that form though, like what if you have a really long polynomial? Just use your polynomial long division. And it's still gonna work, okay? Let you know, I'll have them downloaded either by today or tomorrow at the latest. You're gonna be okay. Next, we're gonna start on 6.1 through 6.5. I will move all the homework probably the following Monday. That gives us a dedicated whole week to finish up chapter 6. 6.1 and 6.2, uber easy. 6.3 and 6.5 get a little weird, but they're okay. Okay, more the word problems are the last ones that are gonna be hard. Okay. All right, guys, I will see y'all next week. Remember, there's no class tomorrow.